Hello, everyone. We are graduate students from Northwestern University. Today, Hui-Wen and I are going to talk about imaging painting, which is a very interesting topic of computer vision. So what is the imaging painting? It is a process of reconstituting missing portions of a visual medium, for example, an image. You can remove anything unexpected in an image and then restore its background. Here come the challenges. We hope the restored gap be structurally consistent with the overall image. And in the meanwhile, we don't want any trail left showing there used to be a gap. Since 2000, many researchers have spent time on this through non-learning methods like diffusion or patch-based approaches. With the advancement of deep network, learning-based approaches involving convolutional neural networks became popular after 2015. Another interesting thing to mention here is its metric. Though many perceptual motivated distance metrics are proposed, they often fail to explain many nuances of human perception. So the best way is still through human observers. The very first attempt is the diffusion-based method using evolutional update. During each update, we try to shrink the target region to be filled through computing content and the direction. The direction is a tricky part. It can be the normal of boundary, which is really intuitive, but this does not work well since the region to be filled can be arbitrary. You can see the images on the top right. If we fill in the white area based on the boundary normal, the result will be unexpected. The solution is to use isofault, which is orthogonal to the largest spatial change at each update, thus ensuring the smoothness of propagation. However, this method only considers the closest pixels as references, and it can be improved through combining texture synthesis. Compared to diffusion-based approaches, example-based approaches perform better on larger gaps since it has a better way to handle texture synthesis. Let's see the bottom right images. We have a target region to fill and first select a target patch to do the texture synthesis. Then we find several patch candidates in figure C and copy the best matching patch into the selected patch. Another important thing to consider is the filling order of these patches. It can be based on the local smoothness or incoming structures, which are confidence and data terms in the bottom equation. These approaches fundamentally rely on low-level cubes, which are less effective for images with larger structures. One important issue is that they cannot handle frontal parallel scenario, as you can see on the right. One impressive solution is to use guidance-based methods involving patch offsets. To be specific, it finds out similar patches in the known region, and their relative positions are offsets. These offsets form a statistical distribution where the dominant ones describe how patterns are most possibly repeated. This is really helpful for us to fill the missing region since it really computes and captures the global structure. A powerful improvement upon this is to include planar structure, which makes this method more comprehensive. People always try to recover the missing area through information from the known regions. It can be the neighboring pixels, patches, or even the global structures. But Inpainting is not deterministic, and it's always possible that something beyond the known region is inside the missing area. One approach is to use external datasets. We can retrieve semantically similar images from a large dataset and copy a single large region to fill the missing pixels. Another approach is to apply interactive inpainting and let the user become the generative tool. As you can see in the top right images, user specifies a structure through a curve, and then algorithm helps propagate it through copying patches. The rest of the missing part is completed through texture propagation from neighboring regions. However, this technique is still not fully automatic. We now turn into learning-based methods, which tends to be more generative.
Since 2015, many deep learning methods have been proposed. Most of these algorithms are based on convolutional neural network, which is powerful in capturing image features. UNet is a widely used architecture in segmentation tasks, which is closely related to image inpainting. UNet is based on the encoder and decoder architecture to do the pixel-wise prediction. Recently, generative adversarial networks have shown its power in generating images. Many approaches are based on GAN. We can divide the learning-based approaches as GAN-based and non-GAN-based. Compared with the classical approaches, the learning-based approaches can generate novel pixels because it can learn from the large dataset. It can also capture the global structure and fill in large missing regions because of the convolutional neural network. Image inpainting for irregular hosts using partial convolution was proposed in 2018. It is based on UNet encoder and decoder architecture to learn the feature. Some previous work may suffer from the artifacts, that is the color discrepancy and blurriness. To solve this problem, this work used a partial convolution, that is to limit the convolution only to valid pixels and then update the mask. The result showing the picture shows its power in generating the novel pixels and fill in the large gaps. Context encoder is the first GAN-based algorithm. It is also used the encoder and decoder structure. The encoder can capture the context features and decoder can generate the missing regions. It can generate the novel objects and fill in large missing regions. The objective of context encoder is to minimize the loss function, which consists of the reconstruction loss and the adversarial loss. The reconstruction loss is used to control the overall structure, and the adversarial loss is used to make the image more realistic, that is to improve the resolution. Many other approaches have been proposed to improve the consistency, coherency, and resolution of the result. For example, by using a global and a local context discriminator, the global discriminator can improve the consistency and the local discriminator can make the boundary more coherent. Also, a coherent semantic attention layer can be added to model the semantic relevance to improve the coherency. Other approaches are best to improve the resolution problem. For example, by combining the context prediction with the texture network, the texture network can improve the resolution. And adding high resolution residual image is also a way to improve the resolution. And another way is to iteratively generate images, then output the confidence feedback, then improve the resolution by the iteratively. Future direction includes reducing complexity of algorithms, achieving more diverse results. In some tasks need more results than a single image. Video is also a more complex task because it has to achieve both spatial and temporal coherency. That's all for our presentation. Thank you for your listening.